Hello everyone. In this notebook, we are doing a thorough side-by-side comparison of five different early stopping strategies. First in TensorFlow and Keras, then in PyTorch, so you can see exactly how each one behaves when a model starts to overfit. And those five techniques are naive, early stopping plus restore best rates, LR, reduce on plateau, cosine, and annealing. Cell 1 consists of setup. We start by importing NumPy, Matplotlib, TensorFlow, and PyTorch. We then fix all random seeds to ensure reproducibility, and we set three key constraints. 80 total epochs, so early stopping has room to kick in, a batch size of 128, and a training set of only 8,000 CIFR10 images. We deliberately kept the training set small so the model overfits quickly, making the effect of early stopping very obvious in the plots. In the next cell, we load CIFR10 normalized pixel values to the 0 to 1 range and wrap everything in a TF data pipeline with shuffling and prefetching. The CNN we built is intentionally slightly over-parameterized to conventional block with 64 and 128 filters followed by 5 12-unit dense layer so that without any stopping mechanism, it will overfit to the small training set. That was the data we have taken. Then in the next cell, we train the same architecture 5 different ways. Strategy A is the naive baseline, no stopping callbacks at all. The model runs all 80 epochs and validation accuracy platters and eventually diverges from training accuracy, which is the classic sign of overfitting. Strategy B adds early stopping with the patience of 5. If validation accuracy does not improve for 5 consecutive epochs, training halts. In our run, this fire at epochs 13 and saving the equivalent of 67 weighted epochs. Strategy C uses early stopping with a patience of 8 and restores best weight. Best weight is equals to true. This means that even though the trigger fires at epoch 25, the model's weights are automatically rolled back to epoch 17, where validation accuracy was at its peak. Strategy D combines reduce LR on plateau with an early stopping callback. Whenever the validation losses stagnates for 4 epochs, the learning rate is cut in half. You can see this happen repeatedly in the output log. Only when the model stops improving, even at a very low learning rate, does the early stopping callback finally fire. In strategy E, we add a model checkpoint. Model checkpoint callback that saves the best model to disk on every improvement. After training completes, we reload that checkpoint with load model and confirm the final validation accuracy, giving us a safety net that is completely independent of in-memory weight restoration. In the next cell, we do the side-by-side plots shows all 5 training. Let me show you the plot. The plot shows all training accuracy and validation accuracy curve on the same axis. Dotted vertical line mark the epochs where each experiment was stopped. You can immediately see that the naive run diverges the most, while the restored best strategies end at higher validation accuracy despite stopping much earlier. Moving ahead, we now replicate all 5 strategies in PyTorch. Because Kira's callbacks do not exist here, we write our own early stopper class from scratch. On every epoch, it compares the current validation accuracy against the best score seen so far. If there is no improvement for more than patience epoch, it restores the save weight using copy.deepcopy and load state dict, then return true to signal the training loop to break. The 5 PyTorch experiments mirror the TensorFlow ones exactly. Naive, patience 5, restore best, reduce LR on plateau combined with early stopping, and finally cosine annealing warm results. combined with early stopping. The cosine scheduler is unique to PyTorch here. It periodically restarts the learning rate on a cosine curve, which can help the optimizer escape local minima before the early stopper fires. Next, we have, as you can see, all the five. Then we have PyTorch comparison plot. Again, we can compare the train accuracy and validation accuracy by the PyTorch. The vertical line again signifies is the epochs where the epoch stops. Next, we have patient sensitivity analysis. Then we run a quick sweep over four patients' values 2, 5, 10, and 20 to show the trade-off. A very low patient stops too early and the model underfits. A very high patient allows too much overfitting before stopping. The sweet spot in this experiment falls around patients equals 10. You can see here. In the next cell, we have the final cell visualizes the two learning rate schedulers in isolation without any full training run. You can see that reduce LR on plateau produces a staircase. The rate drops sharply each time a plateau is detected. And the cosine annealing worm restarts, by contrast, produces a smooth cosine wave that periodically reset to original learning rate, giving the optimizer repeated chances to escape flat regions. The key takeaway from this key notebook is that naive fixed epoch training is almost always the wrong choice. Adding restore best weights costs nothing and consistently delivers a better final model. This was all about this notebook. Thank you for being here in the video.